Hello everyone, welcome to the third class of this course. So in the past few classes, what we have learned is basically if we are given a second order differential equation, for example, uh, let's say px d2y dx2 plus qx dy dx plus rxy equals to 0, okay, where y is basically a function of x, and this px, qx and rx, these are also the functions of x. So if we are given a differential equation of such kind, then what we have learned is basically we can find a power series solution at some point x naught such that yx equals to an x minus x naught to the power n equals to 0 to infinity. Okay, so now the question is, if you are given such a differential equation, can we always find a power series solution at some point x naught? So like for any point x naught, can we always find a power series solution? So the question is, can we always find such power series solution for any point x naught? That's the question we will try to investigate in this class. So the answer is no. The answer is no. We cannot always find a power series solution at all points, right? For x naught can be anything. So here the statement will be, we can sometimes find a power series solution at some point x naught. Okay. Now depending on whether we can find a solution at x naught or not, x naught can be characterized in two ways. Okay, this point x naught can be characterized in two ways. One is ordinary points, and other is singular points. Okay, define what do points. So x equals an ordinary then qx. So what is this qx? Qx is this coefficient, okay? So this is the qx, this is px, and this is rx. So qx divided by px and rx divided by px, both are analytic at x equals to x naught. So by analytic, what I mean is basically around x equals to x naught, we will always find a Taylor series expansion of these functions qx by px and rx by px. Okay. So what we need to check whether x equals to x naught will be an ordinary point or not is basically that is p of x0 not is equal to 0. So that's what we need to check for the moment. Okay, so to check whether x equals to x0 will be an ordinary point or not, we need to simply check. So the rigorous condition is basically qx by px and rx by px both are analytic at x equals to x naught. But for simplicity, what we need to check is basically whether this p of x naught is 0 or not. So if p of x naught, so p is the coefficient of this y double dash, so if p of x naught is 0, then it's a singular point, it's not an ordinary point. And if p of x naught, so this it's the denominator of this function, so this qx by px and rx by px. So if p of x naught becomes 0, so then basically these ratios, they diverges. So if p of x naught not is equals to 0, only then we will call it as ordinary point. And in that case, the solution will be, so we can write the solution as yx equals to sum over n equals to 0 to infinity a n x minus x naught to the power n. The way we were writing a series solution. So that's the usual method. So we can solve, or we can apply this usual method of finding a power series solution only if it's an ordinary point. And how to check for ordinary points? To check whether this coefficient, so the point, let's say x naught, that will be an ordinary point if p of x naught, if this p of x naught not equals to 0. Okay, and now let's define a singular point, and which is basically the check will be like the rigorous definition will be x equals to x naught is a singular point, is a singular point if qx by px and rx by px, those are not analytic. So either of them are not analytic. But if you want to check for it, so you will simply check whether p of x naught equals to 0. So if p of x naught equals to 0, so if this denominator goes to 0, p of x naught becomes 0, in that case we can just directly say, or simply say that okay, the given point x naught is an ordinary point for the given differential equation. So there can be two types of ordinary points. Okay, there are two types of singular points. So once you have checked, okay, p of x naught equals to 0, so it's a singular point. So does that mean that okay, we cannot solve it, we cannot find a series solution at around x naught at all? The answer is no. There are cases where we can still find a series solution around x naught. Okay, so let me divide it in two parts. So there can be two cases. There can be two cases. One is regular singular point, another is essential singular point or irregular singular point. Okay, so the definition of a regular singular point is basically if qx by px times x minus x naught and rx by px times x minus x naught square both are analytic. So if qx times px qx by px times x minus x naught and rx by px times x minus x naught square both are analytic at x naught, at x equals to x naught, in that case the point will be a regular singular point, and in that case we can find a solution, we can find a series solution of that differential equation at x naught. Okay, so the method is called, so we can find, so let me write it down. In this case we can find a series solution at x equals to x naught, and the solution will look like the solution will look like yx equals to sum over n equals to 0 to infinity an x minus x naught whole to the power n plus s, where s is some constant, no? So this method is called the Frobenius method. So instead of assuming the series solution as yx equals to sum over n equals to 0 to infinity an x minus x naught to the power n, we will assume that the solution will be y as a function of x equals to sum over an x minus x naught to the power n plus s. Okay, where s will be some constant whose value will determine as we solve. So for a given differential equation which is px y double dash plus qx y dash plus rx y equals to 0, if this qx by px, so if this qx by px at x equals to x naught is analytic, as well as if this rx by this px at x equals to x naught is analytic, in that case we can get a series solution which is in this usual form, which is sum over an x minus x naught to the power n. If that's not the case, then still we can find series solution of such differential equations, and so that is only for the case of regular singular points, which is defined like if qx by px times x minus x naught, where x naught is the the point at which we are trying to find the series solution. Okay, so if qx by px times x minus x naught and rx by px times x minus x naught square both are analytic at x minus at x equals to x naught, so in that case the point x naught will be called a regular singular point, and we can still find a series solution of such differential equations where the solution will look like this. Okay, so here this s we will determine as we solve the differential equation. So I will do some examples in the later classes. We will see how to find out this s. So what we need to do is we need to find out in this case this an and s. Okay, this is the Frobenius method of which is applicable for regular singular points, and in this case for ordinary points we need to find out only these ans. Basically here we need to find an and s, and for all other cases, so this will be the essential singular points in, so that is basically when these functions, these are not analytic at x equals to x naught. Okay, so where these functions, this function and these functions, where these are not analytic at x equals to x naught, so then the point will be called the essential singular point. I am not writing it again. So in this case we can't find any power series solution at x equals to x naught. Okay, so if x naught, so the point where we want to find out, so around which we want to find out the power series solution, so if the point is an ordinary point, then we can find a solution. If the point is a regular singular point, then also we can find a series solution. But if the point is an essential point, then we cannot. So how to check whether a point is a ordinary point or a regular singular point or an essential singular point? So in the later classes I will do some examples, and there it will be very clear how to check and how to solve in these two cases. For essential singular point we cannot solve, but in these two cases how to solve, so that in the later classes I will show you the examples. For the moment let me give two examples. So let's take the Legendre differential equation. Legendre differential equation. So how does it look like? 1 minus x square d2y dx2 minus 2x dy dx plus L into L plus 1 y equals to 0. Okay, so here this is our px, this minus 2x is our qx, and this L times L plus 1 is our rx. And so this px, this qx by px, if we want to find okay, so if we want to find, so we want to find series solution at x equals to 0. Okay, so we want to find series solution in like this, a n x to the power n. Can we find that? Okay, can we find it? So in that case, what we need to check is basically qx by px at x equals to 0, whether that is analytic. And what is qx by px? Qx by px is basically minus 2x divided by 1 minus x square at x equals to 0, and this is basically 0. Okay, so this px, so px at x equals to 0 not is equals to 0. So in that case, both this is L into L plus 1. Okay, let me write one more step. L into L plus 1 divided by 1 minus x square at x equals to 0, which is L into L plus 1. Okay, so as both of these functions, these are analytic, so then x equals to 0, we can say that okay, x equals to 0 is an ordinary point for Legendre differential equation. Right, and we can find a solution which looks like to the power n. So these kind of solutions are possible, series solutions are possible. So for Legendre differential equation, x equals to 0 is an ordinary point. Let's take another example, which is Bessel equation. Bessel's differential equation. Okay, which looks like this: x square times y double dash plus x times y dash plus x square minus p square. Let me write it something else, because this p we are using it for some different notation. So let me write it something. U, let's write it u. Okay, y equals to 0. Good. And the question is whether we can find a power series solution at x equals to x naught, x equals to 0. Okay, so this is our px, this is our px, this is our qx, and this is our rx, right? And you can see that px, this px, this px at x equals to 0 is 0. So in that case we can say that okay, x equals to 0 is a singular point. It's not an ordinary point, but we still have hope, because it can be a regular singular point, and in that case we can use the Frobenius method to find a power series solution. So we need to check whether it's an essential singular point. In that case we will not get any power series solution, or it's a regular singular point. In that case we will get a power series solution. So how to check that? It's very simple. So what you need to check is basically qx divided by px times x minus x naught, and this x naught is 0 because we are trying to find 0 equals to, or I can write it as x only. Okay, x naught equals to 0, it's because we are trying to find out a power series solution at x equals to 0. Good. So qx is x and px is x square. Okay, times x equals to 1. So it means this function it is analytic at x equals to 0. Okay, let's check the other one, which is rx by px, and in this case it will be x minus x naught whole square, which is, this is at x equals to 0, is at x equals to 0, at x equals to 0. It means I can put here only x square equals to, what is rx? Rx is x square minus u square divided by px is x square times x square at x equals to x 0, and this x square cancels, so we are left with minus u square, and this is also analytic. No? Analytic at x equals to 0. It doesn't diverge basically or undefined, so it is also analytic at x equals to 0. So in that case, as these two functions, this one and this one, both are analytic at x equals to 0, in that case we can say, okay, x equals to 0 is is a regular singular point for Bessel's differential equation, and we can find a power series solution at x equals to 0 using Frobenius method. Using Frobenius method, and the solution will look like yx equals to sum over n equals to 0 to infinity an x to the power n plus s. Okay, this x naught is 0, so we are supposed to write it like this, x minus x naught to the power n plus s, but as x naught is 0, we will happily write it like n plus s. Okay, and how to find this an as an, how to find this an, how to find this an and this s, that I will do in some later classes, with some example, and also when we will solve the Bessel equation, in that case also we will solve it step by step. Okay, so this is how we can check whether we can at all find a power series solution around some given point. In the next class, I will first do some examples for ordinary points, and then I will do some examples regarding the regular singular points. So where we will use the Frobenius method, so we will use these kind of solutions. One other thing I want to mention, which is related to the last class, basically. So in the last class, at the beginning, I told, so the topic will be, so okay, let me just write it. So what I told is, if a0 plus a1x plus a2 plus dot 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 an x to the power n equals to 0, then all ai are individually 0 for all I equals to 0, 1, 2, dot, dot, n. Okay, and I have proved that okay, this is the case. Now I want to draw some analogy with vector space. Okay, so let's consider two vectors in 2 dimension. One is v1 and let's say v2. Okay, so in that case, any vector v we can write as this lambda 1 v1, any vector v in 2D times lambda 2 v2, right? And now if this equals to 0, so v1 and v2, these are two vectors which are whose directions are different. Their directions are not the same for v1 and v2. And in this case, if v equals to 0, then we can say okay, lambda 1 lambda 2 both are 0. So this is the condition, or in this case what we will say is basically v1 and v2, this v1 and v2, these are linearly independent vectors. Okay, so now I will motivate you to think about vectors not in terms of directions and magnitude. Okay, so if you have done a course in linear algebra, you will see okay, vectors are not just a quantity which has direction and magnitude. It can be a lot of things. There are, so it can be a lot of abstract things, a matrix, set of matrix that can be vectors, set of functions that can be vectors. So in this case, you can see here, this, so this a0 plus a1 x square, sorry, a1x plus a2x square plus dot 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 plus an x to the power n sets of fx. Okay, so where all these coefficients, first this is a0 times 1. Okay, so I can just draw an analogy and write it like, okay, this 1, this x square, this x cube, dot 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 x to the power n, these are linearly independent. because if this term, this equals to 0, so then all these ai's like a0, a1, a2, a3, a4 dot 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 an all are 0. So this can only happen when these functions like 1, x, x square, x3, x cube, x to the power n, these are all linearly independent. Okay, so I will motivate you to think in terms of so in this kind of abstract notation. It will be helpful. If you find it complicated, you can just leave it for the time being, but if you start to think in terms of this language, it will be helpful in later classes. Okay, so what I am basically trying to what analogy I'm trying to draw is basically these functions. These functions, these are acting like vectors. Okay, the same algebra we are using here in case of Cartesian vectors. The same algebra we can map for these functions. Okay, so as we will look at the solutions of this Legendre or Bessel or Hermite differential equations, so then things will be much more clear. I am not expecting you to appreciate this part like at this moment, but try to keep it in mind and try to think in terms of this language. Okay, so that's all for today. In the next class I will try to solve some differential equations regarding ordinary points, and after that I will do some examples corresponding to this regular singular point. Okay, bye.